Okay, welcome. I'm Mike Walter. I'm the director here at the Earth and Planets Laboratory of Carnegie Science. How many first-timers do we have here tonight? Oh, that's fantastic. If you want to know more about Carnegie Science, we are a nonprofit research organization, everything from the deep cosmos to in scale, from deep time, from the origin of the universe to basically, well, a minute ago. That's all of our purview. Our mission is really driven by curiosity and discovery. And so we love to share that curiosity and that discovery with all of you. So welcome. It's really great to have you here. And we have a real treat for you tonight. And before we introduce our speaker, I'm going to introduce somebody who's going to introduce our speaker. And that is our own research scientist here at Carnegie, Mike Wong. Mike, you can come up. Mike is an astrobiologist and a planetary scientist. He studies planetary atmospheres and biosignatures and the origin of life and planetary habitability. And he's been working with our speaker tonight.
All right, thanks, Mike. So it's my pleasure to introduce Dr. Caleb Scharf. Caleb is the senior scientist for astrobiology at NASA's Ames Research Center in Northern California. Prior to that, he was the founder and director of Columbia University's Astrobiology Center. Caleb has had both an illustrious and wide career in astrophysics, ranging from X-ray astronomy to observational cosmology to the origins of life, exoplanet science, and the search for life in the universe. In addition to being an outstanding scientist and a leader in our field, he is also an amazing science communicator. He writes regularly for Nautilus magazine and Scientific American, and in 2022 received the Carl Sagan Medal from the Division for Planetary Sciences of the American Astronomical Society. That's the highest science communication award in our field. Now, Caleb's work, both his scientific work and his popular science writings, have had a huge impact and meaningful impact on my career personally. As a fellow astrobiologist, my goal is to try to seek signs of life elsewhere in the universe. But prior to coming to Carnegie, I was getting very disillusioned with the state of the art of biosignature research. And then I read Caleb's previous book, The Ascent of Information, which talks about the power of information, how information can take on a life of its own. And that book changed the trajectory of my research down a path where I now use data science, informatics, machine learning, and artificial intelligence to supercharge our search for life beyond Earth. And I'm so proud to be a co-lead of a team with Caleb, a team that includes Carnegie scientists Anirudh Prabhu, Bob Hazen, and George Cody, pursuing how artificial intelligence can revolutionize our search for life beyond Earth. But that work has barely begun and will probably be the subject of a neighborhood lecture down the road. But tonight, we're going to focus on Caleb's new book titled The Giant Leap: Why Space is the Next Frontier in the Evolution of Life. And as somebody who has inspired many giant leaps in many young scientists' careers, myself included, I think Caleb is the perfect person, the world's expert in this subject. And I can't wait to see where this giant leap takes all of us. So please give Caleb Scharf a warm welcome to Carnegie.
Is it all on here? Okay. This is not my laptop. It is. Okay. Thank you so much for such a generous introduction. I'm going to be hard pressed to sort of live up to that reputation, I think, this evening, but I'll do my very best. Thank you so much for inviting me here to Carnegie for the evening. It's wonderful to come to this beautiful campus, and it's such an exciting place for all the science that's done here, and for the sort of the atmosphere, the creativity, and the congenial state of everyone who works at this institution. So this evening, what I really want to do is to give you a different perspective on this enterprise of space exploration. Space exploration is something that often gets watered down gets turned into ideas about competition between different countries and different corporations and so on. And what I really want to do is to try to take a step back and give you a much grander perspective on that enterprise and show you why I think it is such a vitally important thing to understand and appreciate in all our lives and in our future lives, or the future lives of what comes after us. But to begin, I thought I'd try to remind us all of the incredible amount of exploration and technological development and adventure that has taken place in space over the last 70 or 80 years. And so this is going to be a very compressed view of some of the things that have happened, just to remind us of what has already been accomplished. So let me begin, and this will go pretty fast, and it will not cover all space history, but it will cover some, certainly the first 3 decades. So space exploration actually began in the 1940s, for real. And that's something that not everyone remembers. But in 1946, the first image of the Earth was taken from space. This is at an altitude of 65 miles above White Sands in New Mexico. And it was taken using a modified V2 rocket that was acquired from Nazi Germany by the sort of budding US space program. 10 years later, we saw the launch of Sputnik 1, the first orbiting artificial satellite around the Earth by the Soviet Union. And in that same year, the first animal orbited the Earth, this unfortunate street dog Laika that was acquired in Moscow and sent into orbit around the Earth. Just 2 years later, we obtained the first images of the far side of the moon. This was the Luna 3 probe again from the Soviet Union. In 1960, the very first weather satellite was launched in the form of essentially a live video feed taken from orbit of the Earth, tuned to the infrared waveband so that we could see the water vapor in clouds. And it was a revelation. 1961, the first human successfully orbits the Earth in a space capsule. Also in 1961, the first planetary flyby, Venera 1 from the Soviet Union, makes a flyby of the planet Venus in the inner solar system. 1965, the first human spacewalks detaches from their capsule. Well, detaches, they were still attached via a cable and life support systems to float above the Earth. And it keeps going. And these are just highlights from these extraordinary 3 first decades of space exploration. 1965 as well saw the first successful flyby of the planet Mars by the Mariner 4 instrument, taking images of Mars and deducing that it is a cold, dry desert planet. Then in the period of time, actually from 1958 to 1969, was the era of lunar exploration. In 1966, we saw the first successful soft landing on another world by the Soviets and the first images sent back from the surface of the moon. Not that long later, in 1968 to 1969, of course, we saw the first human missions to the moon and the first human landing on the moon with Neil Armstrong and Buzz Aldrin. 1971, just a couple of years after the first lunar landing with humans, saw the first space station, Salyut 1, in orbit around the Earth. 1971 saw the first successful orbiter to go into orbit around the planet Mars. This was Mariner 9. Unfortunately, when it arrived, the planet was in the midst of a global dust storm. And so the mission had to pause itself because it really couldn't image the surface of the planet. It had to wait for about 2 months for the dust storm to dissipate. 1972 saw the first mission to pass through the asteroid belt in our solar system. This was Pioneer 10, which then headed off on what is essentially an interstellar trajectory to leave the solar system. 1972 saw the launch of Landsat 1, one of the first of a long sequence of extraordinary space-based platforms that observe the planet Earth, sensing its oceans and its landforms and its plant life and human activity with unprecedented detail. 1974, the first multi-planet interplanetary mission with Mariner 10 flying by both Venus and the planet Mercury. 1975, the first successful landing on the surface of another planet by Venera 9, a Soviet mission on the surface of Venus. So we landed on the surface of Venus successfully and sent images back before we did on any of the other planets in the solar system, putting aside the moon. It's a slightly different kind of body. 1 year later, 1976, saw the Viking missions to Mars and successful soft landing on the surface of Mars and images sent back from the surface of Mars. 1979 saw Voyager 1 visit Jupiter and discover evidence of active volcanism on one of Jupiter's moons, Io, with these enormous plumes jetting up into space. That same year, Pioneer 11 made the first visit ever by our species of the planet Saturn before again heading off into interstellar space. And 1980 saw the launch of the first operational space shuttle, the first reusable spacecraft that our species had produced. And it keeps going. This is just the first 3 decades of space exploration. To date, there have been over 140 lunar missions. Some of those didn't quite work out, but certainly 140 attempts. Over 50 Mars missions. Over 700 people have been in space, and that includes those in suborbital launches. More than 3,000 Earth-observing satellites have been launched. There are well over 100 space-based telescopes and observatories that have been launched to not peer inward, but to peer outward into the cosmos and the universe and its most distant reaches. And an extraordinary 15 missions have returned extraterrestrial samples, have returned samples from other places in our solar system to the Earth to be studied and scrutinized in places like the Carnegie Institute, back here where we have our remarkable laboratories. Right now, there are some 45,000 identifiable human-made objects orbiting the Earth. There is as many as 140 million smaller objects, pieces of space junk orbiting the Earth. There are 36 active solar system missions. That includes missions on the surfaces of other worlds or places like asteroids. And of those 36, 9 are currently active missions at the planet Mars. There's a lot going on. But what does this mean? What does this really telling us? Well, what it's telling us is something is happening. And for a while, that perhaps wasn't quite so clear, although when you see everything accumulated like I just did, perhaps it feels like a lot has been happening. But something new above and beyond what has happened is taking place right now. We're seeing a near exponential growth in the number of objects being launched to space from the surface of the Earth. There are roughly 30 launch sites across the surface of the Earth. And this is in part driven by companies like SpaceX and their reusable launch systems and others like Blue Origins and Rocket Lab and so on. But it's not exclusively that. And it's not exclusively the United States. Other countries are doing this too. Something is happening. We are launching more and more things into space. Well, this is where we need to step back for a moment and ask ourselves, what does this really mean? It is something extraordinary. It hasn't been going on that long. It appears to be accelerating in pace. What does this mean? Well, as Mike mentioned in his introduction, I study astrobiology, questions about the nature of life in the universe. And so an obvious question that these observations raise is what happens, what really happens when life moves beyond its planetary origins? We seem to be witnessing a moment where that is truly happening. What are the grander implications? And why is this happening? Can we say something about that comes from a higher perspective, a broader perspective than the usual parochial sort of squabbling perspective of us humans trapped on the surface of a planet? Well, My answer is that I think we can gain that perspective, and that's what I'm going to try to share with you this evening. And that perspective comes from considering the natural history of space exploration. We usually think of natural history of life on Earth, but what about the natural history of space exploration? Can we look through that lens and gain something of understanding of what is happening today? Well, I would argue that to really understand the natural history of space exploration, you actually have to go back to the beginning, or at least the beginning of this solar system, some 4.5, 4.6 billion years ago. Our solar system, the sun, its planets, the other materials, essentially condensed out of a collapsing cloud of interstellar gas and dust, a nebula. And that process formed the sun, it formed the major planets through the coalescence or accretion of material, driven primarily by gravity as well as some other processes. So 4.5 billion years ago, we had the major planets of this solar system. And of course, one of those is of particular interest to us, the third planet out, which is the Earth. So let's track the Earth through time to get this grander perspective. Well, one thing we know for sure is that the Earth has been many different things throughout the last 4 to 4.5 billion years. The outward appearance of the Earth has changed dramatically. Its environmental conditions have changed enormously. It has been an evolving world. So early on, it may have even been, it may have seemed as if it were an ocean planet with hardly any large land masses. Its atmospheric composition was very different, certainly very, very different right at its point of formation, but then quite different again from today, a few billion years or a couple of billion years into its history, an atmosphere full of carbon dioxide, possibly at times a larger amount of methane, nitrogen, and so on. And things changed. And one big dramatic change was the oxygenation of the Earth's atmosphere, the rise of oxygen-producing organisms, photosynthetic organisms that produce molecular oxygen essentially as a byproduct, as a waste product from their metabolism. That oxygen gradually entered the atmosphere. It changed the chemistry of the atmosphere. It changed the chemistry of the surface of the planet. It changed the chemistry of the oceans. And in fact, the gradual oxygenation of the Earth's atmosphere, starting some 2 or so billion years into the history of the Earth, or some 2.5 billion years from today, that oxygenation and the changes it wrought on our planet may have at certain times helped destabilize the climate state of the planet, allowing it to fall into states of global glaciation or so-called snowball events, where much of the planet may have froze and the average temperature was below the freezing point of water. But life persisted. And once again, the planet pulled itself out of those glacial conditions when they happened and continued to evolve. Continents and oceans change their configuration until we arrive at the Earth today. But there is something that is common across all of those periods in Earth's history, which is that the Earth remained a largely closed system. Some atmosphere leaked to space. Occasionally it was hit by asteroids that might have ejected material from the surface of the planet, but otherwise it was a closed system in terms of the matter that came in and out of the system, apart from some leakage and the occasional asteroid impact. And that's interesting because all that started to change in a different way in 1957. And this is an animation, greatly exaggerated in terms of the scale of the objects, showing that sometime around 1957, the Earth started expelling pieces of itself without an asteroid impact to do it. These pieces just started appearing in orbit around the planet. They weren't sailing off in random directions. They seemed to be intentionally placed in stable configurations around the Earth. This is a very strange thing. It's such a perverse thing. The planet, after all, 4.5 billion years ago, went through all that effort to accrete itself out of interstellar matter, turning gas and dust into a coherent solid, a coherent ball of minerals and other compounds. And here it is now undoing that. It's undoing itself, sending parts of itself out into space, and not just into orbit around itself, but across the solar system. Some of that expelled matter has visited the sun, it's visited the major planets, the moons of some of the major planets, visited asteroids, and some of that expelled matter is now heading out into interstellar space. What a strange planet. What on earth is going on? And of course, those expelled pieces, which are of course the product of us, of a particular species that has arisen on the planet, those expelled pieces are enormously complex. Each one, and this is just a cross-section of some of the spacecraft that have been launched over the last 70 years. Each one is complex on the macroscopic scale. There are solar panels, there are spacecraft structures and buses and radio antenna and so on. They are also extraordinarily complex at a microscopic level in their computer chips and their sensors. And they all are constructed from the elements of the Earth, whether it's things like carbon and oxygen and nitrogen and sulfur and so on, or metals, or some of the rarest elements on Earth. They have been brought together, structured in these enormously complex forms and spat out into space. How strange. What does that mean? Well, one thing it has meant, and this is just one example, is that for the first time in 4.5 billion years, stuff that exists on the Earth is now somewhat connected to stuff that exists elsewhere in our solar system. These are images of the planet Mars, real images, landscapes that look not dissimilar to the American Southwest, and then close-ups on the lower right-hand corner where you see mineral concretions in the Martian soil, the sort of thing you would see under a magnifying glass. These extraordinary images are now part of us. By sending stuff out into the solar system, that expelled matter has connected this world to other worlds in quite a profound way. And of course, it's doing that through us, through the human species, but is nonetheless a connection that has not existed before in the entire history of the planet Earth. So what does that mean? Well, what I'm going to try to argue is that it means there's an enormous transition taking place, and has been taking place since the first launch to space. A transition point in the natural history of life, as well as the natural history of space exploration. And the interesting thing about major transition points in the history of the Earth are that they are often also about changes in what is possible in the future. And this is particularly true for the phenomenon of life. So I mentioned the oxygenation of Earth's atmosphere. Well, of course, the oxygenation of Earth's atmosphere eventually enabled other life to exploit that oxygen, and to exploit that oxygen by respiring it, by incorporating it into their metabolic processes. That's what we do, right? And oxygen respiration is a chemical powerhouse. It provides much more chemical energy in cells. It enables more genes to be expressed. It enables cells to replicate more rapidly. It enables faster evolution. It enables multicellular life to arise. So it changed the range of possibilities available to life, the oxygenation of Earth's atmosphere. And other transitions, like mass extinctions in the history of life on Earth, can be seen as opportunities. What's bad news for one species is great news for many other species, because new niches open up. And I would argue that space exploration is a major transition, and therefore it is about changes in what is possible. So now I want to try to unpack that a little bit and talk about the scope of those changes. And this is where it's helpful to have some parallels from the history of human exploration, some other stories to look at and to consider what they meant for the trajectory of our species and the trajectory of life on Earth, and what that tells us about the changes afoot because of our exploration of space. So this is a picture of a very famous ship. This is the HMS Beagle. And in the 1830s, the HMS Beagle set off on a planetary voyage. It sailed around the world for a total of about 5 years. And it, of course, took a young Charles Darwin with it. And the story of the Beagle is interesting in a number of ways when we're looking for clues to what space exploration means for us. And some of those clues and parallels are kind of simple, and some are much more profound and fundamental. Now, the simple ones are things like, a ship like the HMS Beagle in the 1830s was very, very similar to modern spacecraft in many ways. It was a technological marvel. I mean, it had to be. It was setting out on a planetary voyage. It was equipped with the latest gadgetry. It had copper plates to conduct lightning away from its important structures. They changed the iron cannons to brass cannons to reduce the effect on Earth's magnetic field, which would otherwise cause their compasses to be less useful. It carried 22 chronometers, 22 timepieces, in order to maintain accurate and precise timekeeping as they sailed around the world, because that was the way that you navigated in longitude, was by looking at the clock. By knowing what time it was back in Greenwich in England, you could deduce what longitude you were at. And you could, of course, navigate for latitude using the stars themselves. The crew was carefully selected. There were generalists and there were specialists, people all chosen to serve a certain purpose in this complex machine that was sailing around the world, gathering data, supporting its crew with, essentially a life support system, and adapting to changes, adapting to events, adapting to things. It's very much like the process that we employ to design and construct and launch and operate modern spacecraft. But that's the simple parallel to modern space exploration. The more fundamental one is to do with Darwin. So Darwin was exposed to, I would claim, one of the first types of overview effect that anyone can have. So astronauts will talk about the overview effect, that orbiting above the Earth and spending a little time staring out of the window as the Earth spins underneath you gives this sense of unity, a sense of recognition of the integrated nature of everything on the planet and the inseparable nature of everything on the planet. There are no borders separating countries from space. Those are artificial things on maps. And that overview effect must have been something akin to what Darwin and others in the crew experienced. They saw the whole planet. He saw different environments with different species. He saw similar species in different environments. He saw the wealth of life and land and ocean that the planet has to give us. And of course, he used that insight later to develop his amazing Origin of Species and his deep insights into a theory of evolution driven by variation and natural selection. And of course, there were famous examples in the voyage that helped inspire that later work, including the study of the finches on the Galapagos Islands. They're all finches, but they are all also subtly different from each other, and sometimes not so subtly different from each other. They are all as much a product of their environment as they are a product of their immediate ancestry. Darwin put all these pieces together to come up with a theory of evolution. But the interesting thing about that theory of evolution is that it then changed the course of life on this planet. In a very real sense, it caused an evolution of evolution. It was a transition point. That understanding changed the possibilities for evolution in the future. So from Darwin's notes on a tree of life on the left here, where he was thinking about the attrition of life and the diversification of life, people were led to think about organisms in a new way, about inheritance. And then they went on a quest to find the physical mechanisms of inheritance in eventually the decoded structures of molecules like DNA and RNA. And that profoundly changed our relationship to how we breed our foodstuff, how we grow our plants and handle our livestock, and how we think about our own trajectory in the world. And it created concepts that were mapped into things like economics and psychology, the nature of evolution, adaptation, and environmental change and selection. And now, of course, those same ideas have given rise to gene editing tools, which really, really do change the course of evolution if they're applied. They fundamentally alter the possibilities of the future. So not only that, those ideas are behind many of the deep concepts used to develop modern AI. Your ChatGPT owes some of its existence, whether you like it or not, to Darwin's ideas, to the idea of feedback-induced change and adaptation. It is how these algorithms learn. It's how they learn about data. It's how they learn to do things. So I would argue that the journey of the beagle, Darwin's experience, that exposure, that connection to new information about the world, set in motion not just his theory of evolution, but that theory in turn then changed the range of possibilities for life on this planet through us, because our actions impact all other life on the planet. So, what about space exploration? Well, I think the equivalent story for space exploration actually starts even earlier. It goes back to the rise of this species that has this trait of analytic thought. And it has that trait, it has a strong trait for analytic thought. And thought is what you needed to start with to allow life to break free of its planetary origins. Because you needed a concept of nature, of the fact that there is a physical reality. You needed things like cosmology, which is a description of the structure of that physical reality. You needed to understand the nature of motion in the world and to begin to quantify that. You need to understand the notion of forces in the world, forces that can change motion. You need to understand concepts like momentum, which is to do with moving objects in their mass. You need to understand the conservation of certain properties in the world, including things like momentum and things like this characteristic that we call energy, these things that describe the propensity of things to happen in the world and how those things happen in the world. We needed all of these concepts in place. We, of course, needed the idea of gravity, gravitational force that Newton gave us, a quantification and evaluation of this mysterious thing that keeps us stuck to the surface of the planet. And one reason why I can't just jump and head off to space this evening, apart from a ceiling above me. We needed all of that, and we needed the things through mathematics into the calculation of motion in gravitating systems in the form of orbits. And we needed things like the principle of least action, which basically tells us why things tend to move in a straight line or take the shortest path between. And all of those things are also connected to very fundamental ideas of symmetry in the universe. So symmetries in why things are the same, for example, yesterday as they are today. Physics do not change between yesterday and today, as far as we know. That symmetry between yesterday and today in the law of physics is actually what gives rise to the conservation of energy. And you need to know all of these things in order to take your rather crude flight rockets that actually get you where you want to go and actually place you in orbit and actually take you out to Mars and to Jupiter and to other places. And the other human trait that is connected to our analytic thought is human imagination. We are a species that is awfully good at extrapolating from what we know to things that all those things had to be in place for life to get free of its planetary origins. And what a change it has made. Perhaps we don't always think about this much. We've become sort of numb to it if it's not on our Instagram feed these days, or if it's not on a newspaper headline, we sort of forget that space has and is completely changing the distance back on Earth, and through us, the nature of existence for everything on Earth. We have navigational systems, GPS systems that pinpoint all of us in this room. If you have a phone in your pocket, you know where you are. The system allows us to design transport networks for our food, our goods, and other things around the planet in a way we could never have done before. It helps us know where to plant our crops and monitor those crops. We can track other species around the planet and through them learn things about environmental changes that are taking place on scales that are hard to easily measured. The planet has profoundly changed land use by us and therefore by other species. In fact, remote imaging of Earth has placed hundreds of billions of dollars into world economies because of what it enables us to do in terms of making decisions and understanding our own urban spread and so on. And of course, we can use data from space to predict the weather and climate, which is enormous. And not just economically, it changes the nature of our existence. It changes the decisions we make at the microscopic level when you and I decide what to do today because of the weather, all the way up to the decisions of countries and of entire populations. And as we've traveled out into and information back, we are, as I already said, connected now to places that life was never connected to before. We are learning things about bodies that give us insight to the functioning of our own planetary body, the Earth. We're also learning about the origins of these worlds. And we're learning about the sun, a long overlooked object in our sky in terms of what its impact on us is. It's not just about feeling hot. The sun is an active star. The sun sends material out across the solar system. There are solar storms. They light up beautiful aurora, but they can also completely destroy our technological world. And we need to be cautious about that. We need to monitor the sun. We need to understand it. And space is allowing us to do that and to be better and better at dodging solar storms and the damaging things they do. But it goes deeper than the mission that's taking place. There's change in the possibilities that are available to us and to all life on Earth. There are hints reshaping of the solar system. Just the beginnings, just the tiniest hints of the beginnings of something that may play out over hundreds, thousands, tens of thousands of years. It may seem trivial, but there are astronaut footprints on the moon, in the lunar dust. There are tracks left by our robotic rovers on Mars. There is a large habitat orbiting the planet right now that contains a sort of ecosystem that's capable of supporting human life and other life. And then we are actually moving natural objects around in our solar system. This is a time-lapse image from an extraordinary experiment and mission that took place in 2022 when a spacecraft was used to attempt to divert the motion of an asteroid. These images are just before it hits the no more. That's why there aren't any more images after a certain point. That mission, in fact, it hit a moon of an asteroid, but that moon of an asteroid is basically also an asteroid called Dimorphos. And it changed, the impact of that spacecraft changed the orbital period of Dimorphos by about 32 minutes as it slowly tracks around its parent body or its primary body. That's remarkable. Now, this was a test of potential technology for diverting asteroids from hitting us and destroying human civilization. So it was, really to do more than to show that we might be able to protect ourselves from asteroids coming to hit the Earth. What this did was reshape part of the solar system. And in fact, later calculations have shown that some of the material ejected from that impact may have fallen down on the surface of Mars as meteorites. So some unsuspecting future Martian, maybe a descendant of ours, may see these beautiful meteorites flaring through the Martian sky and wonder what's going on. Well, actually, humans did that. We set that in motion. So there are hints of an actual physical reshaping of the solar system. We are also far from done in knowing how to get around the solar system, in how to spread into the solar system, how to explore it. There are emerging forms of interplanetary transport. And that's very interesting because it means this process has not completed by any stretch of the imagination. So there are things that are called weak stability boundary trajectories, which doesn't sound very exciting. But it turns out that in a complex gravitational system like our solar system, where you have many planets and asteroids and moons all exerting a gravitational pull on any other mass and on each other, and all in constant motion, in orbit around the sun, in orbit around each other, our ideas of trajectories, orbital trajectories, gets complicated. Orbits aren't just circles or ellipses. There are pathways that you can follow in this complex dynamic space where you can actually use the natural gravitational landscape to take yourself from A to B using very little energy. And this is very much like sailors on the ocean, using the currents and the winds to get themselves from one place to another with the least effort. It turns out there's very similar things that you can do out in space. And that's really fascinating because it changes the whole scope of what we can do. With very little propulsion, very little energy, you can send spacecraft on really interesting paths through the solar system. One way to think about it is they find those places between planets or moons where the forces of gravity of two objects sort of cancels out. There's a little window of opportunity. You can slide through that space without being unduly pulled in one direction or another. That's essentially what's going on here. In fact, the mathematics is really quite complicated. And you need computers to do things like this. And you might even need things like AI to do this efficiently. AI that owes some of its existence to the ideas going back to people like Charles Darwin and the nature of evolution. But we are deploying these techniques. The graphic here shows a mission called Bepi Colombo, built by the European Space Agency and the Japanese Space Agency, that should enter into orbit around the planet Mercury next year, in 2026. It will enter orbit not with a grand flaring of its rockets and all sorts of theatrics and fireworks, but it will enter using one of these weak stability trajectories. It will literally allow Mercury sort of gently pull it into orbit around itself. It will fall into orbit around Mercury. Not only that, this spacecraft utilizes a still emerging form of propulsion that we call an ion drive, an incredibly efficient form of space propulsion that only works in the vacuum of space. It doesn't exert that much force, but you can have it switched on essentially endlessly for months and years and so on. In fact, the force of an ion drive is about the same as if you put a sheet of paper on your hand and hold it there, which doesn't feel like very much. But you keep exerting that force in space for long enough, and you can build up enormous velocity. We're learning how to do these things. Things continue to evolve and change. And the trajectory seems that we are going to be what I call, well, we are going to be spreading further and further into the solar system. Okay, I have a couple more things to say before I finish. On a slightly more technical note, all of what I've just shown you suggests that the way we conceptualize a solar system or planetary system that has interplanetary life, because that is what we are now. The ways we conceptualize these systems may need to change, to evolve. Now, in astrobiology, in this field that Mike and myself are so invested in, where we're looking for an understanding of life in the universe, we get very interested with characterizing planetary systems because we want to understand our own planetary system. We also want to know in planetary systems around other stars where the most likely places are for life to have originated and be sustained. And so traditionally we talk about concepts like the circumstellar habitable zone. Okay, this green patch that I put here. And what that really is just a range of distances from a parent star, where if a planet like the Earth is orbiting in that range, its surface temperature has a chance of being temperate, of being between the freezing and boiling point of water, for example. And water is so essential for terrestrial biochemistry that we think that's a potential marker of interesting worlds. And of course, the Earth lands more or less in that circumstellar habitable zone, that not too hot, not too cold region. We also think in our own solar system about when it gets colder further from the sun, it gets cold enough that water ice can exist in a vacuum without dissipating, without sublimating. And then you can form these things like the icy moons of the giant planets like Europa and Enceladus that we believe quite strongly have interior liquid water oceans capped by ice. You need to be able to have that ice cap to contain and allow for those liquid water oceans. This is traditional. This is now, well, it seems crazy to say it's traditional because we've only been doing this for the last 30, 40 years. But this is kind of how we look at planetary systems today. But we should probably be thinking about characterizing planetary systems that have interplanetary life. Because maybe the best way to sustain life for a long period of time is actually for it to be interplanetary, for it to not remain stuck in its point of origin, to spread out and do different things. So this map would look slightly different. Instead of just the circumstellar habitable zone, we might have a zone to do with solar storm risk, a zone to do with cosmic radiation risk, a zone to do with ease of transport. You know, how easy it is to change your orbit, to exploit that interplanetary transport network and get around in a planetary system, where you get the best solar power, or where it's easiest to obtain solar power, and where the asteroid resources are. Where are the raw materials in a planetary system? This is a different way of thinking about the suitability of a planetary system for life. But it, I think, is important because maybe life often does this and becomes interplanetary. Okay, I'm almost done. I just want to spend the last couple of slides talking about an idea that tries to pull all of this together. So when I was writing the book, you know, talking to my editor, editors like you to, get to the point, help the reader, don't make the reader work too hard. And so I tried to come up with a term to describe some of what I'm getting at, this idea of major transition, this idea of new possibilities for the future. And the word I came up with was dispersal, because that's kind of what's happening here. Life that started in one place is beginning a process of dispersal. And the thing about this is when you start to think about dispersal, it's very hard to predict exactly how this is going to play out, right? It's a fool's game to predict anything, in my opinion, in the world, unless you're extremely certain. And especially for things like space exploration and the future of technology, we keep getting surprised. But in science, what you can do is find the boundary conditions, set the limits. You can understand how far certain phenomena can get to in scale, in temperature, in complexity. It doesn't matter. You can set some bounds. And that's useful because within the bounds, then you can play around with possibilities. And so what are some of the bounds to dispersal? So what you'll see on this slide may seem utterly ludicrous, but it actually is about realistic bounds and limits. So one thing about dispersal is that the scale of our solar system and its resources, the physical scale of our solar system and its resources, are far beyond anything life on Earth has previously engaged with. The Earth is a big planet. There's a lot of stuff. There's a lot of organisms. It's had a long time. Absolutely. The solar system makes that look like nothing. The solar system is a whole different order of things in scales, physical scales, in scales of causality, the interconnectivity of things because of the finite travel speed of light, and resources. So an example of a calculated boundary condition is shown here. And this looks kind of silly. It's the sort of thing you write on a cocktail napkin after too many drinks, and scientists sort of go, oh yeah, that's great, ha 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 ha, and smoke a pipe and all this sort of stuff. But it's actually not an unreasonable thing to do because it tells us something about the limits. So you can actually take our data on all the asteroids in our solar system. These are the smaller leftover chunks of material from that epoch of planet formation some 4.5 billion years ago. We have an idea of that population thanks to the work of astronomers and astrophysicists and so on. And we also have some idea of the composition of those objects, the different abundances of different elements like carbon and oxygen, nitrogen, phosphorus, and sulfur, elements that are an integral part of life. And you can just do the calculation that just the asteroid material out there, asteroids in the asteroid belt, other asteroids that occupy space between the planets almost everywhere in our solar system, if you took all of those, and I'm not explaining how you would do this, who knows, but it doesn't matter. The point is to establish the boundary. If you took all of those, you could, just using asteroids, form 6,000 Earth-sized biospheres out of that material, in addition to the one biosphere that we have on the Earth. And 6,000 Earth-sized biospheres could support something like 50 trillion humans, scaling from the number of humans currently supported by one biosphere. It sounds absurd, right? This is sort of a Jeff Bezos dream, right? Or Elon Musk dream. Well, they are onto something because these are the bounds. And you might say, well, that's ludicrous. We can barely get enough electricity to charge our iPhones or, charge our Teslas or what, well, I shouldn't say Teslas, or charge some sort of EV that you might have in your garage. How on earth could you power 6,000 biospheres and 50 trillion humans? Well, easy. The solar system is abundant power, abundant energy. The sun, less than 0.0003% of the sun's total output would power all of that. No problem. So, if that is part of the future, and it's not going to be the immediate future, right? Hundreds of years, thousands of years, who knows if we make it that far. What does that really mean? And this is my last slide. This is where I think it gets interesting and actually kind of hopeful, because some of this veers into the sort of tech bro, yes, we're going to conquer everything, never mind political correctness. But I think there is something hopeful and interesting and rather beautiful about this, because we know what the consequences are for life when it is dispersed on the Earth. Okay, and a great example of that is the Galapagos Islands again. The Galapagos Islands, these geologically relatively young land masses onto which species have dispersed, spread from other continents and so on. And as they've dispersed, they've encountered different environments, different niches, and they have changed. They have speciated. A single species becomes many species. They have diversified. This is often called adaptive radiation in every. And so maybe that is part of our future, and the future of any life that leaves its planetary origins behind and disperses into its solar system, is that it becomes diluted, it becomes separated. For a moment, it doesn't quarrel so much because it's too hard to quarrel with someone that is separated from you by billions of miles. And it changes. So the future is not us. The future is the species that we become. And I personally find that quite hopeful. Okay, the very last thing I will say. Often when we talk about space exploration, especially given everything that's happening in the world, an objection arises, which is it costs a lot of money and it's ignoring the problems back on Earth. And I have great sympathy for that. Absolutely. Yeah, it does cost quite a bit. It's not as much as that, but it does cost a lot. And there is a shift of attention. But I don't think space exploration is really about ignoring Earth's problems. In fact, it is in part about dealing with Earth's problems. But more than anything, what space exploration is, what this crazy, remarkable journey that we've been on for the last 70 years already, what it is about is creating chances for us to do better. And I'll stop there. Thank you.
Thank you so much, Kim. That was absolutely fascinating. We're going to open this up to questions. Mike and I will walk around with our catch boxes. Please raise your hands and we will toss a box your way. There's one over there.
Thank you for the talk. I had a curiosity about the theoretical aspect of plane. I know the mass, the total mass of the asteroid belt is only a small percentage of the Earth's moon's mass. So I was wondering how you could make 6,000 Earth-like biospheres out of that.
Yeah, it's a great question. So the key thing here is that Earth's biosphere is formed essentially out of a thin bit of the top of Earth's crust. And just in terms of mass, that isn't that much. It's a tiny fraction of the total mass of the planet. And it's a small fraction of the total mass of the moon. So I think that's really the simplest way to look at it is that, yeah, the Earth's biosphere, which is this rich thing that seems so deep and pervasive, is still just this veneer on top of the Earth. So the numbers do actually work out. Where?
So you kind of talked about the history of Earth exploration as sort of a parallel to what we could see as space exploration. And if you kind of look at the history of Earth exploration and what we've seen as space exploration with like a root underlying aspect of international competition, sort of, who's to say that we're not, do you think it's inevitable that we wouldn't bring those same issues into space exploration, like, for example, trying to put borders in space?
It's a great question. I think, unfortunately, yes. There's going to be some aspect of that. That's already been the case and is currently the case. A lot of what's driving current discussion about the US space program is the concern that other countries like China and so on will get to certain places first and do things first and what have you. I think, yes, we're not going to totally escape that. However, part of what I was trying to get at with this idea of dispersal on a truly grand scale is there may come a point where actually that kind of squabbling and competition becomes less relevant just because of the sheer scale of what we're dealing with and the separation and the sheer amount of resources, that it becomes less beneficial to fight over something because you could just go over there and get it. Right? Maybe that's overly optimistic, but I think part of what's going on here is there is a transition in thought from resources of the Earth, which, while enormous, are nothing compared to these resources in the rest of the solar system. And so for a time, at least, Perhaps before you get 50 trillion humans who might actually be squabbling over things because there's too many of them. There may be a period, and it could last thousands of years, tens of thousands of years, where perhaps we prevent our worst nature from fully taking control. I'm trying to be optimistic. I feel the world needs a bit more optimism at the moment. But I think it's a great point. You can't. One thing we've learned is it's really hard to engineer human nature. But you can make people sit in different corners for a while.
Thank you.
Yes, please. Yeah.
First, it was wonderful. And I even heard you kind of agreeing on the optimistic side. So I want to present the other side. If you look at the history of our species, which is one of many other species that don't exist anymore, but within the history, our history of our species, things don't seem to go linear. We have evolution, but we have a lot of branches that die out. We have a lot of unexpected things beyond disease and just internal turmoil, because of too many people, not enough organization to deal with the numbers of people we have. So my point being is, if you look at history and you see the ups and downs of everything almost, I mean, 99 or whatever percent of the species that ever existed disappeared. Doesn't that put a little bit of a damper on your optimism, so to speak?
In the sense that we might not last long enough to really do some of this? Is that what you're getting at?
Yeah.
Sure. Yeah, I mean, that could be an outcome, that could be a trajectory. But I think, it doesn't have to be the trajectory. Luck plays a role. And, one of the things that I find quite difficult with, considering the history of life on Earth is that we know so little about it that we may be kind of skewed in terms of what we think ends certain lineages, right? We don't know the whole story. Yeah, I think if it were easy to look at the potential futures for us and say each single one is a dead end, right? Then you could say, sure, we're screwed, right? But I think that isn't the case. It's possible to look at possible imagined futures for us, whether they're optimistic or more muted, and say, well, yeah, that might be difficult, but there does seem like there is a possibility of sort of getting through that bottleneck to something else. So I prefer to think there's still a chance.
The optimism is good for our own existence.
Right.
Yes, thank you. You mentioned the syncreticity of reason in figuring all this out, but isn't imagination really the rather mysterious precursor to it all?
Well, I did mention imagination. Sure. Yeah. I mean, yeah, I think that's a fair point, right? What motivated people to come up with the idea of nature? What motivated people to come up with a cosmology or to concern themselves about how things move around in the world? Absolutely. I suspect imagination probably did play a big role because but I think it is part of our type of analytic thought, right? That capacity to conjecture, the capacity to hypothesize. So yeah, maybe it's all owed to, every youthful human being playing with a stick, throwing it up in the air. Oh, it came back down. What if it didn't, right?
Caleb,
Yeah.
There's a question from Zoom. Barbara Bald asks, I want to believe that we'll make things better through exploration, but we can't seem to be doing that environmentally here. What is to say that we don't make it worse out there too? This is very similar to Abby's question. So maybe I'll spin it in this direction. How do you think that space exploration, which does have some environmental damage here on Earth, but what do you think we'll learn by doing space exploration that might even be able to improve our life here on Earth, the environmental status of our own ecologies?
Yeah, it's a great question. So I think, I mean, this is just one possible response to that. One of the things that we do know about space is it's hard, right? I know I've sort of glossed over that to some extent. Isn't it amazing all the things we've done, and look what, we could become 50 trillion humans. Space exploration is really, really difficult. I mean, I'm speaking personally here, but I do work for NASA, and I know it's incredibly hard. There are a lot of hard problems. And some of those hard problems are to do with using resources very, very carefully, even given the number of resources in the solar system. At a microscopic level or at an individual level, you still are going to have to be incredibly efficient in how you use resources, and how you use energy, and how you do things, and how you grow your food, and how you monitor your health, and so on. And I think that does have lessons for what we do back on the Earth, for sure. It has lessons as well because it's an example of really having to live that life, right? I mean, I know we could all go off and join a commune and grow our carrots and not wash our clothes ever and so on, and feel better about ourselves, maybe. But, it's not the same as, living in a space station or going out and learning how to create a habitat on an asteroid or on Mars or whatever, because there you really are having to invent new things all the time, right? And so I don't know if this is a particularly crisp answer to that question, but I think part of what is to gain is challenging ourselves with stuff that's really, really difficult to do. Whenever we do that as a species, well, okay, sometimes we just kill ourselves, right? But in other times, we actually do learn how to do remarkable things and to take it a little bit further to the next level.
Yeah, so I'm going to kind of ask you about, we're in another kind of hinge here with the development of artificial intelligence. And so not just the amazing ways you're using it to do science, but in more, the amazing rapid development of its capabilities. And so I'm kind of wondering, you see humans spreading as physical entities throughout our solar system, but it kind of raises the question of whether, in fact, AI initially developed certainly by humans would be a more effective mechanism to spread through the solar system. That's question one. Question two is, you're looking at life beyond our trying to find life beyond our solar system. How does that factor into your kind of also looking at our life spreading through and expanding in the solar system? And how does those two things inform each other, or that maybe they don't, in what you're doing and how you think about it?
Two good questions. Let me start with the second question. I sort of alluded a little bit to that when I talked about these zones in a planetary system. There are zones that we associate with perhaps greater probability of origination of life and sustainment of life over time. And those are things to do with environmental conditions, right, on perhaps the surface of a planet. And we map those things out to exoplanetary systems as a way to try to prioritize places to look. Say, well, this system has a planet that is potentially habitable, right? But what we're really talking about there is this idea of That's where life might originate and be sustained. I think life that goes beyond its point of origin does change that equation. And we haven't really started doing this yet. You know, we have a little bit in terms of thinking about technological structures that might be placed in a planetary system by a species that has done this, has become interplanetary, and whether we can see those things using our space telescopes, using new technology from here, whether those things, those artificial signatures of life. I mean, artificial is a tricky word here. It's sort of, I think of it more as a natural extension. Whether those might be more or less amenable to our detection. So it plays a role, but we're just starting to figure that out, starting to peel that apart. Your question about AI, I think, is a really excellent one, and it's something I know I think quite a lot about. I know Mike thinks about. I didn't really get to that because that felt like adding a bit too much to what was already a lot of stuff in the presentation. But yes, absolutely. We already know that human space exploration must be technologically supported, right? We die otherwise. You need a spacecraft. You need all the mechanisms around you to sustain you, to help you navigate, to help you go from place to place, to breathe, to eat, to so on and so on. That's not going to change right away. And even when if we build artificial habitats, you know, bigger space stations or habitats on an asteroid or Mars or whatever, that's going to continue to be true. I think it may well be, and we're sort of seeing this with the science already, that AI, or you know, AI is kind of a blanket term, but machine learning and AI may be absolutely integral to enabling individual humans or groups of humans to do all the things they have to do to survive, as well as do interesting things. And so I think, yeah, that interplanetary dispersal is probably a mixture of biology, machines, AI, controlling it all. AI are patient in principle, at least they seem to be. You can make them patient. They could be, you know, the things hauling cargo around the solar system. You know, why have humans do that? You wouldn't have humans do that. You have autonomous agents. You know, we talk about agentic AI now as having these systems where you can essentially make a request or give some instructions, and it goes off and spends hours or days performing different tests and analyses before coming back to you with an answer. That seems like a reasonable thing to be able to do with space exploration. I'd love to have a system where just before it launches, I type in, okay, I'd like you to go to Mars, I'd like you to do this, I'd like you to unearth this rock, I'd look under there, make a decision about what to do next, tell me whether this scientific theory is correct or not, and report back when you're done. Off it goes, you know, I go and have a holiday somewhere, and then, you know, however long later, maybe a year or two later, the data comes back and it's been a scientist for me. Now, it won't, I don't think it will be, we're nowhere near the point where it could be as adaptable and imaginative and as sophisticated as a human scientist, but for certain things, we're getting awfully close with the AI we have now. Attaching that to actual physical mechanisms like a spacecraft or a rover or a mobile lab, that's kind of the next piece of this, I think. So that's a long-winded answer to it. It's a really interesting topic.
One more question from Zoom. JN Nambi asks, curiosity is what starts exploration, but it quickly gets replaced by greed. Is greed going to interfere with our appreciation of space?
Almost certainly. Yeah, you know, I mean, I think one of the problems in the past with people talking about, you know, a future in space and what could happen and so on is not allowing for all the undesirable qualities of humans. I think we have to face those head on. And so, yeah, sure, there'll be greed. you know, sometimes that can be good. I mean, I don't mean in the sort of 1980s Gordon Gekko greed is good way necessarily, but, you know, it too is a motivator. And greed does motivate some things in a direction that ultimately benefits more people than it disadvantages people.
Okay, I think we're going to call it there.